All right, in 6.2, we are still talking about sampling distributions, but specifically we're looking at the center and the variability of a distribution. Okay, so back to the general idea. When using a statistic to estimate a parameter, remember, a statistic comes from a sample, parameter is a population value. Different samples from a population will produce a different value of the statistic. The basic fact is this, it is called sampling variability. The value of the statistic varies in repeated random sampling. We've seen that in many simulations we've done in class. Your sample comes out differently than mine because that's called sampling variability. And because every sample is a little different. So to make sense of sampling variability, we asked what would happen if we took many samples. Well, here's the picture. Here's the blue is the big population. Each little green circle is a sample coming from it, okay? And does each sample reflect the population? What happens if you do this over and over and over? What happens to all these sample values? Okay, for instance, if I was taking, let's say I was taking an average of my samples, whatever it is. I'm trying to estimate an X bar here, an X bar here, an X bar here, an X bar here, so on and so forth. We could do this many, many, many times, and then we would take the mean, the mu, of all the X bars. We averaged all the averages of our samples, okay? So if we do this over and over and over, we're going to do a good job of better estimating what the population value really is. So what we get is called an unbiased estimator. Here's the definition. A statistic used to estimate a parameter is called unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. The mean of its sampling distribution is equal to the value of the parameter being estimated. That means if I'm trying to predict the mean of a population, then the mean of all my means from my samples is going to be equal to whatever the population mean is. And that's because we've chosen an unbiased estimator. It means it's going to be really close to the real value. Okay? So the design of a statistical study shows bias if it would consistently underestimate or consistently overestimate the value that you want to know when you repeat the study many times. So you don't want to trust an estimate that comes from a biased sampling method, and we talked about that before, biased methods. We don't trust those. So we're going to focus our energy on unbiased methods. So here's what's happening, okay? To get a trustworthy estimate of an unknown population parameter, you start by using a statistic that's an unbiased estimator. This ensures that you won't tend to underestimate or overestimate, okay? So what's an unbiased estimator? Unbiased estimators are a mean is an unbiased estimator, X bar, or a proportion, okay? Other statistics we could use that might be biased would be like a range, or a median might get biased. Okay, those are more likely to be a biased estimator, so we focus our energy on means and proportions. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual value. So here's what's happening. Look at this histogram. If this is a sample size of 100, notice how spread out things get, okay? It's still normal in shape, but they're pretty spread out. Look, the range goes from 0.22 to 0.52, all right? Now, if I do 10 times that many samples, and with 1,000 samples, and I take the mean of all those samples, whatever it is I'm estimating, look what happens to my histogram. It got really, really, really skinny, and the range of values got very, very small, okay? So here's the bottom line. Write this down. The sampling distribution of a statistic will have less variability when the sample size is larger. And you want that. You want less variability because it's going to better estimate what it is we're trying to predict. All right, so we can think of the true value of the population parameter as a bullseye on a target, and the sample statistics that we look for as an arrow fired on these targets. Okay, so look at this. Both bias and variability describe what happens when we take shots at the target, right? So in this first target, it has high bias, meaning it's missing the mark, it's missing the bullseye, but it has low variability, meaning they all missed the bullseye in the same place. Look at this one. This one has low bias, meaning they're getting close to the center, but it's high variability. They are spread apart. They're not clumped together. All right? So bias, write this down. Bias means that our aim is off, and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. We need it to center on the right value, but that's what happens when you have bias. They don't land where they're supposed to. Now, look at the third target here. High bias, meaning it completely misses the mark, but it's high variability. They're all kind of spread out. They're not clumped together like they were over here, where they're really, really small variability. And then lastly, this is our ideal target. We want to have no bias and low variability. No bias, meaning we hit the target, and low variability, meaning it really wasn't spread out, everything clumped together. This is what we want, okay? So write this down for high variability. What does that mean? It means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results, okay? So here's what your problems might look like today. The manager of a grocery store records the total amount spent in dollars for each customer who makes a purchase at his store during a week. The values in the table summarize the distribution of amounts spent for this population. So notice on our table over here we have, look, there's 749. Here's the mean, the standard deviation, the minimum, the median, the maximum, and maybe you remember Q1 and Q3. 25th percentile, 75th percentile. So to investigate if the sample median is an unbiased estimated population median, they did the sampling 1,000 times, using 10 in each sample. They were selected from the population of 749. Okay, so they took 10 people at a time. They took the median of that sample and they plotted it. Okay, and that's how we ended up with this dot plot. The mean of the sampling distribution is indicated by the orange line. So let's look at the orange line. Where is it? Well, it's right here, which is around 23. Okay, approximately 23. All right, that's the mean of the sampling distribution. Does the sample median appear to be an unbiased estimator of the population median? Well, how do we know? We look at what our dot plot tells us. Where's the mean of all of this? And compare it to the actual data. 22.96 is the actual median. We came really close to it, 23. So we would say, yes, the mean of the sampling distribution is very close to, what was it, 22.96, which is the value of the population median. The mean of the sampling distribution is very close to the actual population median, okay? Number 2, what would happen to that sampling distribution of the sample median if the sample size were 50? Now remember, the sample size on the previous slide was only 10. So we're taking that sample size of 10 and doing it 5 times. So we're making a much bigger sample size, okay? What would happen to the sampling distribution if it were that? There would be much less. Remember that graph, our curve, which was like this, becomes more steep, okay? So what's happening is our variability is going way, way down. There would be much less variability in the distribution, okay? So what am I referring back to? I'm referring back to this slide right here. Look, we said at 100 samples, look how broad that distribution was. But if I do 1,000, it got really tall and skinny, which means the variability went way, way, way down, okay? So going back to my question, B, what is the practical consequence of this change in sample size? Well, if there's less variability, that means my estimate will be even closer to the real value, okay? The estimate for the population mean the population median in this case, will be more precise. That's what less variability will do for us, and we want that. All right, look at number 3. A study of health teenagers plans to measure blood cholesterol levels of a simple random sample of 13 to 16-year-olds. The researchers will report the mean X bar from the sample as an estimate of mu, the population mean. Right, number 3, a study of health of teenagers plans to measure the blood cholesterol levels of a simple random sample of 13 to 16-year-olds. The researchers will report the mean X bar from their sample as an estimate of mu, the cholesterol level in this population. So explain to someone who knows little about statistics what it means that X bar is an unbiased estimator. Okay? Unbiased estimator. Remember what the visual of the target. Unbiased means you're hitting the target pretty consistently. Okay? You're hitting the target pretty consistently. So how would we write this? I would say the X bar is an unbiased estimator of mu because it does not consistently overestimate or underestimate the population mean value. Okay? X bar is an unbiased estimator of mu because it does not consistently overestimate or underestimate the population mean value. Okay? It lands right where it's supposed to on the target. Okay? It's not perfect, but it's pretty darn close. All right? Hopefully this gives you some model answers as you work your problems, and we'll see you in class.